Hey and welcome. Today I'll be introducing the periodic table. Just a quick basic intro. We're going to be talking about its purpose and how to read it, and then they'll give us the ability to use the periodic table. The first temptation in this video might be to just simply show the periodic table. So there, I did it. But I'm going to save that for last. I feel like there's a number of things we have to talk about first before we can navigate that properly. All right, so let's go. So what is the periodic table? What's its purpose? It's an element organization system. So that means we're going to have to define what an element is. So an element is a collection of atoms, all with the same number of protons. As I'll say a number of times, the number of protons an atom has is the most important and the most fundamental property of an atom. It's the property that tells you what element is what element. Okay? I'm going to say this a bunch of times throughout all my videos, hopefully. For example, we see with carbon, it has a 6 above it. Carbon, by definition, is an atom with 6 protons in it. If I try to sneak in another proton into the carbon, if I was successful doing that, I could not call it carbon anymore. It would now be called nitrogen. All right? So it's all about the protons, right? And all atoms of the same element are going to have the same properties, same chemical reactivity, same appearance and bulk, same everything. Except there is a possible slight difference in masses due to having a different number of neutrons. We will talk about that more when we get to isotopes. But basically, it's easiest to think of all atoms as being exactly the same, except possibly the masses. All right. So how do we read an element tile? So I talked about carbon earlier, and there are 4 components that go into a tile. All right, pause this video if you have to get a right or look at all this, but I'll describe each here. So the first thing is the number up at top. That is called the atomic number, and that is given a symbol of a capital Z. I write my Z's with a line through it so it doesn't look like a 2. So Z, again, that's your number of protons. It's your P+. All right. So in a neutral atom, your Z, your atomic number, which is your number of protons, is also equal to your number of electrons. If you have something called an ion, that means you gained or lost electrons. Okay, that's what we're usually talking about in chemistry. It's the sharing, gain, or loss of electrons. A lot of chemistry has to deal with electrons. We don't mess with the nucleus too much in most discussions of chemistry. That's more of a topic for nuclear chemistry or nuclear physics. So when we just say chemistry, in one sense, we're really talking about electron chemistry. Electrons are the main currency of chemistry. All right, we'll talk about ions more at another time. All right, next we have the element symbol. Element symbols follow a format of having an uppercase letter. And if it has a second letter, not all of them do, but if it does, then it will always be lowercase. For example, a common element is chlorine. Chlorine has a capital C and then a lowercase l. A common mistake is to make the C capital and the L capital, right? So if you're typing that out on a computer, you're going to have to let go of shift before you hit the L. All right, then we have the name. And the name, well, it's the name, all right? And each element has a history behind its name, makes for some interesting reading. Now, again, the number of protons is the most fundamental property of an element. So that means whether you're talking about element number 6, something with 6 protons, something with the symbol of a capital C, or the name carbon, all of them are referring to the same thing. The last bit here is called the atomic mass. Some call it the relative atomic mass. It means the same thing. it has units of atomic mass units, or it has units of grams per mole, which is also known as molar mass. The units will be a focus of another time. I like to call this a weighted average atomic mass, or sometimes I'll just say average atomic mass, but what I really mean to say is a weighted average atomic mass. So, Josh, why are you talking about averages and weights and stuff? Maybe the word weight might be a little bit much for now, but what I mean by average is each element, like I talked about earlier, might have different masses. Okay, this is a phenomenon known as isotopes, which will be the next video. But the long story short there is some carbon atoms may have a different mass compared to other carbon atoms. And so, for example, on Earth, we have to take an average of all the possible weights, masses, whatever you want to call it, and then we report that average. All the word weighted mean when we say weighted average is you have to consider that for some isotopes, some atoms, isotope just means a possibility of different neutrons. For some atoms, some of these isotopes, they're going to have, let's say for carbon, we're talking about carbon, 99% of carbon, about 99% is carbon 12, whereas about 1% is carbon 13. And so you can't just take 12 and 13 divided by 2. You get 12 and a half. And that's not the actual, average, weighted average weight. This is taking into account that most of the carbon is that form of carbon 12. Okay. That's a little preview for my isotope video. All right, so that's the element tile. All right, so how about the organization? We have groups, they're columns, also known as families. There's 18 columns, or depending on who you ask, maybe they might say 32. That's kind of my opinion, actually, but teaching 101, I'm not going to talk about that too much. You'll see why in a minute. I would say there's 32. But for most chemists, they just stick with 18. For periods, those are the rows. There are 7 rows, okay? So when we talk about navigating the periodic table, we have groups and we have periods, okay? All right, so we're almost ready to show the table, but I haven't fully answered the question of why we have a periodic table in the first place. I did mention it's an organization system. Let me show you the power of this organization system. So right here, we have a list of different compounds. These are chloride compounds, chloride salts. The most famous being sodium chloride, also known as table salt, rock salt, halite, halite, however you want to pronounce it. All right, the stuff that you put on your food. So we have all these different chlorides. We have lithium chloride, sodium chloride, potassium chloride, rubidium chloride, cesium chloride, and francium chloride. And you can see on the left-hand side of the periodic table, there they all appear. Hydrogen we'll just leave out of discussion right now. But here are those 6 alkali metals. You can see, looking at all these chemical formulas, that there is one of each of those alkali metals in the chemical formula. You may be like, how do you know it's a 1? I know we haven't talked a ton about chemical formulas yet. In chemistry, if they don't write a 1, if they don't write anything, you will know that it's a 1. It means it's a 1. Okay, so we have 1 of all these metals, and then we have 1 of all the chlorides. If you're curious where chlorine is, there is chlorine. And the point I'm trying to make is all these compounds with the alkali metals have 1 each of the metal and the chlorine. It has that same repeat behavior. So that's where the word periodic comes in. Periodic meaning a repeat behavior, repeated. Okay, so every row is a period, meaning after you finish that period, you start over with a new row, a new period, and you have a repeat story of very similar behavior. Okay, kind of reminds me of going on a typewriter and then it's at the end and you have to hit it back to start the next row on the typewriter. All right. So in a similar line of thought, then, we can look at group 2, the alkaline earth metals is what it's called. And now you can see that whatever that metal is, whether it's beryllium, magnesium, calcium, strontium, barium, or radium, it forms compounds where you have one of the metal and two of the chloride. Okay? So very similar behavior. And we're going to see very similar properties looking at any elements across or up and down the same group. All right, so there were those metals. All right, now I'm not going to talk about every group here today, but let's skip over to group 13. That'll be the last one I'll discuss for this video. So in group 13, we have an aluminum there. I didn't talk about boron there, but we have an aluminum there. And aluminum forms a compound with chlorine where you're going to have 3 of the chlorines for every aluminum. So I could pose a question, gallium being right below aluminum, what would you predict that number to be? And we would put a 3 because we used a periodic table that had predictive properties. All right, maybe it felt a little scary writing that guess. Chemistry has a reputation for having exceptions to things. And that is true at times, but the periodic table is here to give us a predictive power, a good first guess for how things will be. All right, and indeed gallium does form a compound with 3 chlorines. All right, so that's the purpose of the periodic table. All right, so here it is. I got this from ptable.com. Right, you can see the 18 rows or columns, man, 18 groups, 18 families. Some of them have special names like pnictogens, chalcogens, halogens, and then this last group is called the noble gases. In between, we have the transition metals as we're transitioning from the left side of the periodic table to the right side of the periodic table. Okay, a transition. And then this part is called the inner transition metals, goes by a variety of names, and each row actually has a special name, the lanthanides or lanthanoids, and then we have the actinides or the actinoids. All right, now the way I like to follow the periodic table is just follow the number. For me, that's the way I make the best sense out of it. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, so on and so forth. All right, and you keep following the numbers. No, I wasn't going to do every single one, unless you wanted me to. But 55, 56, now check this out. We go to 57 here, 58, 59, da-da-da-da-da-da-da-da. Okay, 71, 72. Look at that. We jump back. So you may be wondering, okay, is this actually the best way to fit this here? From a scientific perspective, I would argue this is not the best way. But from a practical perspective, yeah, it's great because we get to fit everything onto a more standard sized sheet of paper. All right, but in reality, the periodic table looks more like this. That part that we cut out in reality is actually a part of rows 6 and 7, period 6 and 7, and we just cut it out so that it fits onto one sheet of paper. Okay, as we'll talk about in a future video, but I'll just give a little preview right now. You can actually play all these sorts of paper games with the periodic table. You can match up how the periodic table could have looked like. Oh, maybe I should have pre-folded this before the video. Oh well. How the periodic table could have looked like earlier on. You can see 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But once we have to fit in more of these elements, you would get something like this. You'd have to make this new section because this 21 here, the scandium, doesn't belong here. Gallium has more in common with aluminum than does scandium. Same thing can be said for titanium. Titanium's behavior is more different compared to germanium. And this story keeps going on and on and necessitated its own section. As further proof of that, you can see now that within this section, you have metals that behave very similarly. Copper, silver, and gold, for example, are all capable of forming +1 ions, losing that one electron. They're also known as the coinage metals, kind of conveniently all here. And so you get these repeat behaviors here. So it made more sense to have a new section. And then with here, it made more sense to have that new section as well. All right. But when you look at the history of the periodic table, you'll see a history of some preliminary good ideas, and a lot of it was really good. Check out the work of Dmitri Mendeleev, the pioneer of the periodic table. But things weren't perfect, and over time, as we discovered more elements and learned more about them, then we got to the periodic table that we have today. So hope this helps. Hope this was interesting. And thanks so much. Any ideas or comments, put it in the chat or comment section. All right, thanks. Take care.